Welcome back, everyone. We are going to get into the next chapter on our syllabus. This jumps ahead into Chapter 9, Sections 9.3 and 9.4 with regard to geometry. Geometry of triangles, perimeter, area, and circumference. In Section 9.3, we talk about the geometry of triangles. The definition of a congruent triangle is a triangle that has those triangles that, when compared to each other, have the same size and shape. The congruence properties are listed on page 467, and there are also some examples there as well. In order for two triangles to be congruent, they have to have a side, angle, and side that are compared to another triangle with the same side, angle, and side, or angle, side, angle, or side, side, side. So, for instance, if you have two triangles, let's say you have a triangle that looks like this, and another triangle that looks like this. Let's just assume that they are identical triangles. This angle and this angle being the same, this side and this side being the same, and this side, this angle and this angle being the same. This would be an example of two triangles that are congruent because of the angle, side, angle property. When you have two angles and the side in between them that are the same, the remaining sides are automatically the same as well. Also, if you had two triangles that had this side, this one hash mark match up with this one, the two hash mark match up with this one, and the three hash mark match up to this one. This would be an example of the side, side, side. All they have sides that match up, so they would be congruent triangles. The side, side, side would be definition of them being congruent. And then lastly, if you had a triangle, two triangles that had the same side, and then an angle, and then the next side being the same, being equal, then they would be also considered congruent, and this would be by the side, angle, side congruence axiom. In other words, if you take two congruent triangles, it would be possible if you took a piece of paper with the triangles printed on them and you cut them out, you could pick up one of them and place it on top of the other so that they would completely coincide. The book uses an example of the triangular supports of a child's swing set, that the two ends of the child's swing set would be congruent because they are exactly the same dimensions. The isosceles triangle is a triangle that has two legs of the triangle, two sides of the triangle that are the same. And this definition takes the place or defines the isosceles triangle. Triangle ABC is an isosceles triangle with AC, the line segment from A to C, equal to C to B. And if D is the midpoint of the base, then the following properties hold: that the angles A and B are equal, angles CAD and CBD are equal. Now what that means is the angle that goes from C to A to D, the letter that's in the middle refers to the corner of that angle. So CAD and CBD are equal. And then angle ADC and BDC are both right angles. So that means that the angle D coming from either the left or the right is basically a square corner. A right angle is a square corner. Similar triangles are pairs of triangles that are exactly the same shape, but not necessarily the same size. This diagram shows some examples. The marks at the corners show that the angles in the corners are the same angle, but the triangles are not the same size, even though the angles are the same. This is why in the congruence theorem there is no such definition of a congruent triangle being angle, 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 because angles could be all the same, and it is possible that they could be congruent triangles, but it's not automatic that they would be congruent triangles. If measures of two angles of one triangle are equal to those of two corresponding angles of a second triangle, then the two triangles are similar. Now, the angles of a triangle, the number of degrees of angle of a triangle, must always add up to 180 degrees. So what this means is if the measures of two angles are equal to those of two corresponding angles, then the two triangles are similar. The third angle is always going to be the remaining value. There's an example on page 469, example 5, that refers to two similar triangles and how they're proving the similarities thereof. So please take a moment to review that for yourself. The Pythagorean theorem is defining the properties of a right triangle. A right triangle is one in which one corner of the triangle is a 90-degree square corner. So if the two shorter legs of a right triangle have lengths A and B, and the hypotenuse, that is the side of the triangle opposite of the square corner of the right triangle, then the formula a squared plus b squared equals c squared. So what that means is the length of that side squared plus the length of the other side squared would equal the length of the hypotenuse, which is the long side of the triangle, of the right triangle, squared as well. So if you know the length of A and B, then you can calculate the length for C. This illustration is very clever and funny, and many of you may have seen this before, but it's not what we're being asked for. Of course, this is a right triangle. The small square box in the corner refers to that angle being a 90-degree or square corner right angle. This would be an illustration of the Pythagorean theorem, and just like in the previous example, A is 4, B is 3. So a squared plus b squared would be 16 plus 9 is 25. So the length of C would be 5. So x in this example would be 5. So if you turn in your book to page 473, let's look at some of the exercises that are in this section. So they give you a diagram. A, B, C, and D are the points here, and it continues on here in a line. So if angle B, that symbol refers to an angle, measures 46 degrees, then angle A measures blank, and angle C measures blank degrees. So they're telling us that B is 46 degrees. They also tell us that this is an isosceles triangle. Isosceles triangle, which tells us that these two legs are the same length. And if these two legs are the same length, and it is an isosceles triangle, then these two angles, by definition of being an isosceles triangle, are also the same. So what we have here is two angles, angle A and angle C. The total amount of degrees in a triangle is 180. So 180 degrees minus 46 would equal 2 times the remaining angle. So let's call this remaining angle, let's use a Greek letter, theta, which is a 0 with a dash through it. So this is telling us that 180 minus 46 is 134, equals 2 times theta. Divide both sides by 2, and we get theta equals 67 degrees. So angle A would be 67 degrees, angle C would be 67 degrees. Similarly, if in number 8, we have the same figure. A, B, C, D. If angle C measures 52 degrees, what is the measure of angle B? Well, remember, it's an isosceles triangle, so these two angles are going to be the same. So if C is 52 degrees, then A is also 52 degrees, and 52 degrees plus 52 degrees is 104 degrees. So the remaining angle, angle B here, would be 180 degrees minus 104 degrees, or 76 degrees. Key here to remember that for a triangle, the total number of degrees of the angles will always be 180. Now, if you jump ahead to number 25 in here, you'll see in number 25 there are two similar triangles. And let's pretend, for the sake of argument, that these are similar looking on here. And you have these angles corresponding to these angles. So they are similar triangles. Number 25 has the side length of 12, 12, and 15. And they say 6A and B. Now for number 25, corresponding sides must be proportional. Okay, so A over 12 equals, this is a 6, not a B, okay, 6. A over 12 equals 6 over 12. So A equals 6, that's pretty straightforward. But what about B? Then B over 15 equals 6 over 12. So we cross multiply here and we get 12B equals 15 times 6. Okay, so 12B equals 90. Divide both sides by 12. Any number divided by itself is 1, so B equals 15 over 2. So 15, actually it's 15 times 6 over 2 times 6. So any number divided by itself is 1. So what you're left with is B equals 15 over 2. So A equals 6 and B equals 15 over 2. Similarly, in number 26, you have triangles. And they say they're similar. You have a 6 and a 9 and an angle. And you have an A. And you have a 3 and an angle. Once again, corresponding sides must be proportional. So A over 6 equals 3 over 9. Cross multiply, so you get 9A equals 6 times 3, which is 18. Divide both sides by 9. That's a 9. And then A equals 2. In this case, you're only asked to find A. You're not asked to find the other unknowns, but you can see how this applies the principles of algebra to and cross multiplying to solving for the unknown. Now, moving ahead to number 36, the height of a lighthouse keeper. The Santa Cruz Lighthouse is 14 meters tall and casts a shadow 28 meters long at 7 p.m. So let's just let's look at what a lighthouse might look like. So this is okay. So it tells us that the lighthouse is 14 meters tall. So 14 meters. And it casts a shadow 28 meters long. 28 meters long at 7 p.m. At the same time, the shadow of the lighthouse keeper, and here's the lighthouse keeper, is 3.5 meters long. And they're asking how tall the lighthouse keeper is. So this is an example of some similar triangles. Okay. So we want to know what the height is, h. Remember, similar triangles have to be corresponding here. So if h is the height of the lighthouse keeper, the ratio of the height to the length of the shadow is the same as the ratio of the height of the lighthouse to the length of the lighthouse shadow. So we multiply both sides by 3.5 so that we isolate the h. So h equals 14 times 3.5 divided by 28. 14 over 28 is a half, so height, or 1 over 2, is 3.5 over 2, or 1.75 meters. So the lighthouse keeper is 1.75 meters tall. So section 9.4 talks about those triangles, similarity, and congruent triangles. And section 9.4, or that was 9.3, 9.4 goes into perimeter, area, and circumference. Now, a polygon is a geographical shape that has multiple sides, from 3 or more. The perimeter of any polygon is the sum of the measures of the line segments that make up its sides. And perimeter is measured in linear units. So if you have a triangle of length A, B, and C, and length is in inches, the total length in inches of the perimeter is length A plus length B plus length C in inches, and so on. And the perimeter of a rectangle with length L and width W is given by perimeter P equals 2 times L plus 2 times W. To illustrate this, this would be like this. If we had a triangle, with length A, B, and C, the perimeter is the sum of the length A plus B plus C. For a rectangle, we have width and length, and a rectangle is the same width at both ends and length at both ends. So you would just add these all together. So 2 times length plus 2 times width equals the perimeter of a rectangle. So for a problem that refers to the length and width of a rectangle, you want to read the problem, assign a variable, write an equation, solve the equation, state the answer, and then check your answer in terms of the original question. It's always good to check your answer. Now, on page 477 and 478, there are some examples on there. But let's look at exercises 1 and 2. So exercise 1, it says we have an equilateral triangle. An equilateral triangle means that all 3 sides are the same length. So let's just pretend that all 3 of these sides are the same. So the perimeter of an equilateral triangle with side length equal to blank inches is the same as the perimeter of a rectangle with length 20 inches and width 16 inches. So they're saying, well, what's the perimeter here? Now it's equilateral, so all 3 of these sides are the same length. So the perimeter of this rectangle is 20 plus 20 plus 16 plus 16. So perimeter is 40 plus 32. Perimeter is 72 inches. So if the perimeter is 72 inches and we have an equilateral triangle here, equilateral means the same. So the perimeter here is going to be the same also, 72 inches. So the individual length, L, would be 72 divided by 3, or 24 inches. So before we jump into area, let's do another example of perimeter. Jump ahead to number 24. Dimensions of a rectangle, page 485. A video rental establishment displayed a rectangular cardboard stand-up advertisement for the movie The Blind Side. The length was 20 inches more than the width. Okay, so here's a poster here. The length equals the width plus 20. And the perimeter was 176 inches. What were the dimensions of the rectangle? So basically what they're telling you is it's in terms of the width. So the total perimeter is 176 inches. If the perimeter is 2L plus 2W equals the perimeter, and the L is the width plus 20, we can solve this in terms of one equation with one unknown. So 2 times W plus 40 plus 2 times W equals 176. Combine the like terms. 4W plus 40 equals 176. Subtract 40 from both sides. You have 4W equal 136. W equals 136 divided by 4 gives you 34. So the length would be 34 plus 20. So the length is 54. So the length is 54 and the width is 34. So the dimensions of the triangular poster that they're showing is 34 by 54. Now that's a perimeter. Now when we're talking about area of a polygon has to do with the amount of surface area that's covered by that polygon. Think about it in terms of you're buying a rug for a room and you measure the room and you have to measure how many square feet or square yards of rug that you would need to cover all the floor in that room. Area is in square units, for example, square inches, square centimeters, etc., where perimeter was in linear units, inches, centimeters, meters, feet, etc. So the area of a rectangle is the formula area equals length times width. The area of a square is the area equals the side squared, the length times the length. Length times the width, but a square is the same. Those seem to be pretty straightforward, but the area of a parallelogram is A area equals base times the height. An area of a trapezoid is 1/2 times the height times the sum of the two bases, and we'll look at an illustration of that in a minute. And then the area of a triangle is 1/2 times base times height. So an area of a triangle is defined in terms of this is the height, this is the base, 1/2 base times height. So if the base were 5, say, and h equaled 4, then the area, and let's say inches, the area is 1/2 times 5 times 4. So it would be 10 square inches. A parallelogram is a four-sided object. This is defined as having a height h, and a base b, the b base being the entire length of the base. Area equals base times the height. So a parallelogram has two sides that are parallel, four sides that are parallel to each other. A square and rectangle are also parallelograms, but they also have the properties of having right angles at the corners. A trapezoid has two parallel bases. They're represented by a capital B for the larger base and a lowercase b for the other base. The height is based on a square right angle for the base. And the area of a trapezoid is given by the formula 1/2 times the height times the length of the two bases. We had talked previously about circles, and the circumference of a circle is basically the perimeter of a circle. The length, it's a linear measurement around the outside of a circle. It's given by either of these formulas. The circumference, C equals pi times d, or C equals 2 times pi times the radius. The radius is just half of the diameter of a circle. And the area of a circle is given by pi times the radius squared, pi r squared. So let's look at some exercises illustrating area. So look at number 10 on page 484. There's a rectangle, a long skinny rectangle, and it has 1 centimeter and 3 centimeters. They give it to you with these little corners, illustrating that those are 90-degree corners. So it is a rectangle. The area of this figure would be 1 centimeter times 3 centimeters, or 3 square centimeters, 3 centimeters squared. And that makes sense, because if you look at this and you had broke this 3 centimeters up into a stack of 3, like a little Tetris symbol, you can see that there are 3 1 by 1 square centimeter sections. Number 14 has a triangle. This triangle gives a height, and it doesn't matter that the triangle is on an angle here. This is 36 millimeters height, and then the base is 52 millimeters, and the area is 1/2 times the base times the height. So 1/2 times 52 times 36. They're both millimeters, not meters. So 52 times 36 times 1/2 is 936 square millimeters. Jump down to number 20. You have a circle. Circle has a radius of 15 centimeters. The area of a circle is pi times r squared, and they say use 3.14 for pi, so 3.14 times r squared, 15 centimeters squared, gives us 706.5 square centimeters squared. So this this tells us, using this formula, about the area of the circle. A little more challenging is some of the area of a shaded portion of a plane figure. If you look at page 487, you'll see, we'll do an example number 67. gives you a circle that's inscribed inside a square. Square has a diameter of 26 meters. So all of these sides are touching. Okay. And then they give you shaded portions here and here. Okay. And they want you to find the shaded portion. Well, if this goes from here to here, we know that the area of the square has sides of 26 meters. So it's a square. So the area of this square is 26 times 26, or 676 square meters. And the area of the circle that's inscribed in there has a radius of 26 divided by 2. The radius is half of the diameter, so the radius is 13. The area here is pi times r squared, or pi times 13 squared. And we'll use 3.14 for pi again. And this gives us 530.66 square meters. So we have an area of a square, area of a circle. We just take the area of the square, 676 square meters, and subtract the area of the circle. And we get 145.34 square meters. So for problems like this, you want to see where the polygon or the circle is falling, and see if you can calculate the area, or in some cases the missing area. So if you had a, I don't know, let's say you had a garden that had certain shapes to it, urns and flower vases and things like that, and you wanted to put indoor-outdoor carpet around there, you can calculate how much carpet that you'd need in the end. So let's look at another example here. Page 487. Number 69. You want to try and determine which pizza is the best to buy. The dimension given is the diameter of the pizza. So number 69 has cheese pizza, where a 10-inch pizza sells for $5.99. A 12-inch pizza sells for $7.99, and a 14-inch pizza sells for $8.99. Which pizza is the better buy? Well, these are the diameters. If we want to look at price per square inch, that would probably give us the best value here. So the price per square inch would be, we'd have to determine what the area is first. So the radius would be half of the diameter. So the radius here is 5 inches, 6 inches, and 7 inches. So the area would be pi times the radius squared. So pi times 5 squared, which is 25. Pi squared, which is pi times r squared, which would be pi times 6 times 6, or 36. And then lastly, pi times 49. Now, if we use 3.14 for pi, the area gives us 78.5 in square inches. So this is the area in square inches. This is 113.04. And this is 153.86. Now we aren't through yet because we have to compare the price per square inch. So the 10-inch pizza would be $5.99 divided by the 78.5 square inches. So that's $5.99 for 78.5 square inches. This gives us $0.076 per square inch for dollars per square inch. The 12-inch pizza would be $7.99 for 113.04 square inches. $7.99 divided by 113.04 gives us $0.0706 per square inch. And then lastly, $8.99 for 153.86 square inches gives us $0.058 per square inch. So the cheapest price would be this one at 0.058 square inches. So the 14-inch pizza is the best buy. So that concludes the section on chapters 9.3 and 9.4. Please take the time to explore some of the other problems and email me if you have any questions. Thanks very much.